So I'm delighted to join you for the session to talk about rapid prototyping in general and the connection to the pandemic in particular. I direct this program, the Center for Bits and Atoms. And let me also note as I speak, this is interactive. So post questions, burning ones will be fed to me to reply as I'm talking. And then at the end, we'll have about 15 minutes for Q&A for this to be an interactive session. So CBA was created to study and break down the boundary between digital and physical. And that included things like we were part of creating some of the first quantum computations. We're part of creating minimal synthetic life, where you design life in a computer. And so literally turning bits into atoms. What's also interesting is the people who did the work. My student Jason built and now runs all the computers at Facebook. My student Rafi built and used to run all the computers at Twitter. And that's because to do that, you can't believe in a sense, you can't believe in computer science. You can't believe in software separate from hardware. They have to take billions of dollars, megawatts of power, tons of mass, and turn it into information. And so you need to deeply integrate them. So against that background, we've been, okay, it's just a little lag to update. Against that background, we've been very busy with the immediate COVID response. And so I want to talk a bit about that, then about the research roadmap beyond it, and come back to how rapid prototyping has a potentially really profound role to play in not just the immediate response, but the recovery from the pandemic. So using CBA's facilities, early on, we were approached about ways we could help with it. And that's led to a really interesting working group of about 150 people, all working on rapid prototyping for the COVID response. And the work we've been doing progresses immediately from personal protective equipment, urgently needed, to instrumentation to help with testing, to technology for respiratory assistance, and increasingly is pivoted to technology to help with the recovery, monitoring, and steps beyond it. In this, we found there's a lot of issues in the do-it-yourself responses that really need research guidance. Things like 3D printers alone can't do much to help with the pandemic, but rapid prototyping can. A good example is right away there was an urgent need for shields to protect healthcare workers. There are lots of versions of 3D printing them. In a collaboration with a number of colleagues at MIT, we found first from particle modeling, from computational fluid dynamics, you really needed to fold the shield around the face to protect all the ways the particles can come in. And then the 3D printed shields were themselves a point for a vector for the virus to get in. That really interesting collaboration to make a kirigami folded shield. So just cutting and folding, eliminating the printing. On the top, I'm showing rapid prototyping of that. Then in the medical testing, among the things that came up was the need to flip it up, ways to make it more comfortable for the healthcare workers, a lot of iteration on that. And then from there, it went into designs that can be made by rapid prototyping, but then could quickly go into die cut for volume manufacturing to make millions of these. And so a lot of research went into simplifying and improving the design, and now that's propagating and scaling. And so there's this connection between running the research on campus and then connecting it for the global impact. And the working group I described has really interesting weekly sessions. It's driven collaborations unlike anything I've seen on campus and around the world to meet the needs of the pandemic. All the work there is posted publicly, and if you're particularly interested in actively participating, contact me and I can connect you more deeply into the program. So to do that work, the most profound implication I'm going to end with today is how rapid prototyping cannot just meet the immediate pandemic needs, but how it can help us recover along a different pathway. And so to tell that story, I wanted to take you through the research roadmap in CBA's work from now into the future, and then come back to the present. So CBA started with an unusual NSF proposal, roughly to assemble one of every tool to make anything of any size. And so we put together from molecular to macro scale tools to make and measure almost anything, an unusual facility. you can view that as a descendant. MIT invented computerized manufacturing in 1952. So this was at the birth of real-time computing. Jet aircraft were just emerging, and there were parts hard to make by hand. And so there's this idea to connect the real-time computer to the machine to make parts. And so that was the birth of computers controlling machines. And really, the state of the art today isn't much different than that. The computer controls the machine with a head that does something. You can view the lab I run at MIT as the successors of those tools. So I had a problem. It would take a lifetime of MIT classes to learn to use those machines. So with colleagues, I started a class modestly called How to Make Almost Anything, just to teach rapid prototyping, and was completely unprepared for the response. Hundreds of students try to get in every year to the class, and they're there not to do a thesis or a startup. Really, they're there to make things. And they did the most amazing projects. Kelly made a device that saves up screams when you're mad and plays them back later. And this is a web browser for parrots. And this is an alarm clock you wrestle with to prove you're awake. And this is a dress that defends your personal space. And every year there was just these fun, neat projects done. And I began to realize the students were answering a question I didn't ask. I was asking how to go from digital to physical. They were really answering why. And to understand why that's so interesting, the real-time computer was a result of the whirlwind. MIT made the first significant real-time computer. That was transistorized at Lincoln Labs as the T. It was commercialized as the PDP. The PDP was used to create the internet. Most everything you do on a computer today was first done with that. This is Ken Olsen, the founder of Digital, famously saying, "Nobody needs a computer at home." There's a little context to that, but he did say that. What happened was when computers became personal, the whole mini computer industry surrounding Boston couldn't make that transition. It wasn't for inventory and payroll, it was personalizing computing. In the same way the students were showing, the killer app of digital fabrication is personal fabrication, not mass production, but production for a market all the way down to one person, very similar to the personalization of computing with the same disruptive impact. So inspired by that, we were then started a project called Fab Labs. A PDP cost initially maybe $100,000, weighed a few tons, filled a room. There were thousands of them, and thousands happens to be the number of cities on Earth. And so for National Science Foundation outreach, initially we set up a mini version of my lab at MIT that's roughly the cost and complexity of a PDP, called a Fab Lab. It includes a 3D printer, but it also includes 10 other tools to go from digital to physical. And with that, you can make everything on the right: boats, bicycles, furniture, consumer electronics, production tooling. That's not a startup, it's not research, it's community labs producing them. And then they accidentally went viral. Lower left, I'm showing the world map of Fab Labs. And there is just about as far north and south as you can go on Earth, rural, urban. They spread over the planet. We didn't plan that, but there's been this viral spread of these labs. These are some of the sites working with at-risk youth in Detroit, with gross national happiness in Bhutan, mixed communities in Israel, Protestant Catholic boundary in Northern Ireland, Alaska Natives. All of these sites are integrating digital fabrication into their communities for a range of transformative impacts. To keep up with that, we started a program called the Fab Academy to do the same sort of education I'm doing at MIT on this hands-on making, but done in a global way. So students have peers in work groups with mentors in local labs, and then we connect them globally. And that's led to a Fab Academy for textile technology, a Bio Academy with a range of colleagues to teach biotechnology. And that in turn has led to some really surprising impacts that I would have never expected from what just started as a rapid prototyping project. This is Barcelona's mayor. Barcelona has a fabulous design sense and over 50% youth unemployment. A whole generation can't work. What's happening in that picture is he's starting a 40-year countdown to urban self-sufficiency. You expect the city to provide electricity and clean water. What they're now doing is they're setting up these rapid prototyping labs as part of the urban infrastructure. They describe it as the city today is a product to trash conversion device. Products go in one side, trash goes out the other. They want the atoms to stay and the bits to travel. So data comes and goes, but the city produces and consumes locally. And if you live in the city, instead of jobs to work to money to employment, you have the means to produce what you consume. A very different relationship between production and consumption. And that profound change, not just a smart city, but a fab city, has led to a number of leading cities around the world joining Barcelona in this initiative to empower cities to produce what they consume. On the left, I'm showing a lab we ran at the Obama White House. That collaboration led to legislation right now in the House and Senate that today there's a notion of universal access to computing and communication as a kind of a right. This bill says access to the means to do digital fabrication is a new kind of right for which we should aim for universal access, initially at the granularity of congressional districts, to empower not a national lab as a billion-dollar facility with guards at the gate, but a new kind of national lab made out of connected local labs. The national labs can struggle to have community impact, startup impact. This sort of brings the lab to the people. So very interesting legislation. If you're interested, you can just reach out to your local representatives or senators to help support it. It's an unusually bipartisan bill. So not just different parties, but also rural, urban, north, south, all the axes you can think of, this spans, and everybody agrees on the value and the impact of it. One of the interesting offshoots of that is there's a number of companies we're working with, like Airbus, Dassault Systems, GE, Chevron, to help them set up these fab labs, nominally as community outreach investment in the communities they work, but with the profound back action. Over and over, we see the idea is they think this is for their engineers to help the community, but as much knowledge goes from the community back to the engineers. And many of the companies found kids in Fab Labs have better access to rapid prototyping than their own employees. So there's a really interesting synergy with large companies collaborating with these in ways that help others, but also help benefit them. To keep all of that growing, we've had to spin off a nonprofit Fab Foundation, a community portal, Fab Labs IO. It's way beyond what I can run from my office at MIT. And my colleague Sherry Lassiter, who manages this program, noticed something interesting. At the top, I'm showing the 5 points Gordon Moore plotted for what became Moore's law. And he projected that transistors would keep doubling on integrated circuits. He projected 10 years. In the middle, I'm showing the 50 years of Moore's law digital scaling. And at the bottom, I'm showing 10 years of these Fab Labs spreading. They've been doubling for more than a decade, growing exponentially. This has come to be called Lass's law for Sherry Lassiter instead of Moore's law. And what it suggests is there's more data than Gordon Moore had. And so you should really take seriously the notion that this is going to scale for 50 years. And so to start thinking about that scaling, computing went from thousands to millions. Millions are the number of towns. That was the era of hobbyist computers, not yet really widely useful, but personal. And so in support of that, we've done a lot of work on developing the machines that make things. And we've spun off a number of companies like Formlabs, that's now worth $1 billion. These are all companies that grew out of making the machines to make more accessible. And we've done a lot of work on the software you use them to make computer design and manufacturing more accessible. But in a sense, all of that's kind of a disappointment. The goal isn't for you to buy the machine. The goal is to make the machine. So this is work on rapid prototyping of rapid prototyping, Fab Labs making Fab Labs. And the current state of the art begins with a parametric machine generator, where you define the parts of the machine, but then you completely change the architecture. So what you're looking at is actually a distributed computer. The machine itself is a distributed computer, and then you overlay with it distributed computing software. And so the machine could add or subtract or have 3 or 4 or 5 axes, and it lets you do rapid prototyping of the machine building. And really what's emerging from that is the notion that it's not just rapid prototyping. A rapid prototyping machine is a kind of a robot. This is rapid automation, making it as easy to make a machine as the project from the machine is coming out of that. That's had a number of applications. One interesting one I'm showing is the National Institute of Standards and Department of Energy have a national initiative for advanced materials, but it's been very limited by the difficulty of testing and developing and modeling the materials. And so we've been taking all of this rapid machine building and applying it to material science to develop open instruments for material science development and measurement, open materials modeling. This loop of rapid machine building applied to advanced materials. And an interesting project emerging is we're helping regions now set up not $100,000 labs, but with the goal of $10,000 labs, we're helping them set up $1 million labs. And so this one is in the south of India, in Kerala. The next one we're doing is in Bhutan. This is a super Fab Lab. It's a Fab Lab that has a series of machines. Each of these machines cost as much as a regular Fab Lab, but these are the kinds of machines you need to make the parts of Fab Labs. And so the thoughtful state of Kerala wants to have hundreds of these accessible to everybody in the state. And so rather than importing all of the machines, we're setting up a super lab for them to be able to make their own machines. And again, the next one we're doing is in Bhutan. You may know that Bhutan is based not on gross domestic product, but gross national happiness. That doesn't mean they're all happy, but it means the goal of the economy is to measure well-being, stress, health, life outcomes, education. But they were limited by global supply chains for what they consume. And so we're setting up one of these super labs in Bhutan to help them make gross national happiness physical, sustainable local production. So to keep going with the scaling, from millions to billions, there's billions of people on Earth. In the history of computing, that's when computers really became personal. And here we've been looking at a fundamental transition from digitizing not just the designs, but the materials. So not just the transition from subtractive to additive manufacturing you've heard a lot about, but really is not very different from what happened in 1952, but the transition from continuously cutting and to discretely assembling, putting codes into the very construction of the materials themselves. That thought began when we were approached by the aerospace industry about how to automate the production of ultralight high-performance structures that couldn't be done with existing advanced manufacturing. That led us to study how you, instead of having tooling the size of a jumbo jet to make the jumbo jet, linking little parts together. And lower right, I'm showing density versus modulus. And by an order of magnitude, we set the world record for material performance by linking these little parts together. By making it sort of digital in its construction, it worked much better. From there, this is a project we did with NASA, and we're doing a follow-up with Airbus, where there's been a long-standing goal to make morphing aerostructures, airplanes that can continuously change their shape, or potentially much more efficient, but the mechanisms were heavy and complex and expensive. And here we turn the whole aerostructure into one of those. Lower left, what you're looking at is the size of NASA Langley's biggest wind tunnel. And this was a large-scale morphing aerostructure made without any tooling, just by linking these little cellular parts together. Here's an example we did with Toyota of a super high-efficiency race car made completely without tooling, just again by taking these little building blocks and coding the assembly of this high-efficiency race car. We've kicked off a similar project with Oldendorf, one of the largest shipping bulk carriers, to use this to meet the very demanding UN goals for the energy efficiency of shipping that it looks like traditional shipbuilding can't get to. And we're revisiting how ships are made and how ship propulsion works using these parts. And right at the heart of that is how you build these. Traditionally, each of the things I showed you, cars and ships and jumbo jets, have global supply chains. But by reducing the design down to these simple building blocks, you can then make these really interesting robots. So this is a relative robot. It's a material robot system. The robot locomotes on the structure it's building. It error corrects by taking steps on the structure. It navigates relative to the structure. And by doing that, a little robot can make big things. And then we've done path planning for swarms of these robots to be able to do construction. So instead of tooling the size of a jumbo jet to make the parts, and then something bigger than a jumbo jet to carry the parts to assemble them, the final assembly can potentially be the only assembly to make these structures. And then there's a really interesting recursion where you can look at making the bigger robots out of parts from even smaller robots. And so this is an assembler. And what it does is it takes a feedstock of just a few part types, rigid parts, flexural parts. And now these are sort of meso to micro scale parts, and then magnetic actuation parts. And what it's building right now, so this is a funny combination between a 3D printer and a pick and place machine. And what it's doing is it's building a micro robot. And so a rigid part is just rigid, a flexural part bends, 2 flexural parts does parallel transport, 4 of those makes a 4-bar linkage, a 1-bit actuator just is 1 bit, but 2 of those can then do cyclical motion. And then from there you can get locomotion and build up complex robots from these very simple building blocks. And so we're looking at how we can build micro robots this way. So to keep the scaling, computing went from 1 billion towards 1 trillion. In the Internet of Things era, we're now approaching 1 trillion devices on the internet. And so if you take the thermostat, like the one behind me, this thermostat has essentially the same capability as the PDP or the whirlwind. It's not a metaphor. There's 1 trillion whirlwinds or 1 trillion PDPs. And so to look at that in the scaling, I'm plotting here the number of elements in a structure you make and the rate you place them. And the red points are state-of-the-art manufacturing. And these blue points, orders of magnitude away up here, about 5 orders of magnitude away, is molecular biology. We're orders of magnitude away from the ability of biology to fabricate. And right at the heart of that is a recursion. So all of life is made out of 20 amino acids. They're unremarkable. They have very simple properties, but by composing them, you make molecular machines. And the most interesting one is the ribosome. And ribosomes can ultimately make ribosomes. It's the molecular assembler that turns codes into structures. And so ribosomes are slow. They can run at 1 molecule a second, but ribosomes can, through a cascade, make ribosomes. And so you get exponential numbers of ribosomes. So you can program that. This is work we did on designing synthetic life with a number of collaborators. This is work we did on nanoscale printing to make environments for cells. But you're limited to the materials of biology. And so in biology, there's a hierarchy. There's a linear chain that's a code. The code turns into a structure of geometrical motifs. Those turn into tertiary structures that can do things like donate and accept electrons. And then that becomes quaternary structures like the motors moving my muscles or the synapses I'm using to think. And so we've been looking at why can't we do that with inorganic systems? We had an interesting DoD proposal to reduce their whole supply chain to 20 parts. And that's not a metaphor. All of life is made from an inventory of 20 parts. And so we're looking at how you take simple parts like conducting and insulating, you need to digitize them into discrete building blocks, like think of Lego, but micro Lego, and then build functions and modules and systems out of them. And so this is an example of one of the micro robots I showed you, but now the robot has an end effector, and this is work we're doing for the robots to be able to make the robots. And one reason to do that is to be able to exponentially ring up capacity. And so any one is slow, but if robots can make robots, you can build exponential capacity on demand. And one is to build scale. From the smaller building blocks, they can compose to make larger and larger building blocks. And so to really reach these limits of the performance of fabrication, you need this recursion, not just of labs making labs, but of systems making systems. And that project has had a really interesting offshoot. We need to put the intelligence into the robots. And so we're building in little building blocks, not of the biggest chips you can make, but of the smallest chips you can make for the intelligence of these robotic systems. And that spun off a project we really didn't expect to be heading towards, which is chip fabrication has become a national critical vulnerability. There's only a few global foundries that can do state-of-the-art chip fabrication. State-of-the-art chip can cost $100 million plus to develop and fabricate, can take a year plus to develop. But when you make a chip, you don't place transistors at a time, you place macro cells of functional units. And so as an offshoot of the microassembly, what we're now studying is taking tiny chiplets, tiny fragments of chip function that each do a simple function, and robotically assembling them to build three-dimensional integrated circuits, not in the billion-dollar chip fab, but with these commodity parts in a tabletop process. And so it's a very interesting way to think about direct write fabrication of integrated electronics, where you can change the integrated electronics to match the application rather than having a standard chip everybody uses. So ultimately then, if you can do everything I've said, it leads to the ability to place billions of parts in complex systems. And so the limitation that finally runs into is, how do you design these? We do so much work on engineering design tools because we break them when we work on these projects. And so the inspiration here is life itself. I'm showing a day in the life of a zebrafish. It starts with 1 cell, then 2 cells, then 4 cells, then 8 cells. It starts symmetry breaking. And at the end of the day, you have the zebrafish. This was the science's breakthrough of the year in 2018. The breakthrough was not understanding it, but just describing it. What you can now do is you can trace the position of every cell, and you can trace the expression of every gene. What's so interesting about this process is your genome doesn't anywhere store the fact that you have 5 fingers. What it stores is the developmental program. And the developmental program has simple notions like break symmetry or climb gradient. And at the end of executing the developmental program, you have 5 fingers. And there's 2 reasons biology does that. One is it's concise. A billion bases can control a trillion cells. But the much deeper one is it's really machine learning. The heart of machine learning is representation. It's not that we can search better, it's how do you figure out how to search. And evolution, the naive picture is wrong. Evolution doesn't randomly change things. Most random changes to the genome would either be fatal or inconsequential, but not interesting. So to go from swimming to walking or flippers to fingers, you need a way for evolution to make interesting changes. And so one of the oldest parts of the genome has what are called morphogenes that control morphogens that give rise to form. And evolution carefully searches over that space where change is interesting. And so as part of that, we've been working in a very interesting project on rebuilding these layers of how you simulate physics, how you represent it. And so it's sort of tautological that when you design my phone, you design the phone, you design the shape, you design the circuit boards. But again, evolution doesn't do that. It doesn't represent the thing. It represents the program that creates the thing. And that crucial abstraction is what makes the complexity of life possible. So you need to represent things, not as the explicit design, but as algorithms, as functional abstractions that lead to the design. Then you need to search over those in these complex spaces. And so as an example, just as a warm-up, we wanted to try to rediscover gears. Gears represent hundreds of years of insight. And what I'll show you, we're driving an inside here, we're constraining here, everything else is free. And there's a layer of physics, there's a layer of this abstraction, there's a layer of evolutionary searching, and it's exploring the space of gears, and it's going through lots of bad designs and eventually finding a way to reach how the gears mesh. And as it runs, eventually they start learning how to mesh smoothly. And so what's interesting about that is we didn't tell it anything about the shape of gears or how gears are supposed to mesh. This is showing evolution versus performance. Green is traditional gear design. In this case, it happens we could do a bit better than that, but that's specific to that case. But what's interesting is we could rediscover something like gear design, not by teaching it, but by assembling all these layers of how you model physics, how you abstract designs, and then how you search over them. And one more interesting thing we found in that project is one of the hardest parts of that is the learning system cheats. It found all kinds of ways to satisfy the letter, but not the spirit of what we wanted. For example, if the gear teeth catch and it goes shooting off by one of the measures we were doing, that counted as better performance. And so there's a crucial role for the human in the loop to mentor the bright but easily distracted pupil, for the human to guide this process towards what you really want it to do. So to start stepping back from this quick tour, I described a roadmap from one Earth, 1,000 cities, 1,000,000 towns, 1,000,000,000 people, 1,000,000,000,000 things, one mainframe, one first whirlwind, thousands of mini computers, millions of hobbyist computers, billions of personal computers, trillions of Internet of Things. Now, the first NC machine at MIT in 1952, today there's thousands of those Fab Labs, roughly one per city. We're aiming towards millions of labs making labs, these machines making machines, billions of these assemblers rather than printers, and then trillions of these self-assemblers where you fundamentally merge the materials with the machine. All of those things exist today, but they range from coming out today to decades in the future. But if you go back to that scaling graph, there really is a 50-year roadmap for, in this deep sense, merging digital and physical. So now what's interesting is if you go back to the founders of computing, they include John von Neumann and Alan Turing. They're credited with modern computing edifice. Von Neumann architecture, which refers to modern processors, he wrote very little about that. The main thing he wrote was this report, and it's a pretty terrible document. He wrote beautifully about other things, but not that. It was sort of a hack to make this computer work. One of the last things he studied that he wrote beautifully about was self-reproducing automata, how a machine can communicate a computation for its own construction. And so that's what he's modeling here. He co-invented cellular automata to study that. It's really getting at the essence of how life works. Likewise, Alan Turing invented the Turing machine as a model for computability. It was never meant to be taken seriously as an architecture. In a sense, it has, which is part of what leads to a lot of computer inefficiency. But the last thing he studied was morphogenesis, how genes give rise to physical form. And so both of these pioneers in computing ended up by studying computing not as something virtual, not as something in the cloud, but something embodied, something physical. And so I've been credited with, and I'm happy to take credit for the observation that computer science is one of the worst things to happen to computers or to science. And by that, what I mean is it's created this fiction that digital and virtual are separate from physical. The pioneers of computing ended their life studying about how they come together. And so we're clearly in a period of an AI revolution. This is an essay I wrote about that. But to understand the AI revolution, it seems like there was an explosion that recently happened. But if you look at the scaling, within the last year or so, the number of ops a supercomputer can do, which is about 10 to the 7 per second, came to match the number of ops a brain can do, which is again about 10 to the 17 per second. And so the computers reached the complexity of a brain. And so we'd be derelict in our job if they couldn't do something roughly as capable as the brain. Sort of the computers caught up to brains just in the basic ops per second. But now look at these numbers. The supercomputer has about 10 to the 15 transistors to do the computation, about 10 to the 16 transistors to store the data. The chip fab making the computer, making maybe 10 to the 4 wafers per month, 10 to the 8 transistors per millimeter, means the chip fab is making about 10 to the 10 parts per second. while you've been listening to me digesting your breakfast, you've been making 10 to the 18 parts per second. You have about 10 to the 13 cells. Depending on where the cell is in its life, it can have 10 to the 5 ribosomes. They run about 1 hertz. And so you're placing 10 to the 18 parts per second. And so the gap between your brain and a supercomputer has closed. This is all in astrophysical units. I'm just counting the number of zeros. But between the chip fab making the supercomputer and biology making you, there's 8 orders of magnitude. And what I've done through this tour is show those 8 orders of magnitude rest on fundamentally digitizing the materials. The properties of digital codes applied to materials. If you, let's see, compare a Lego brick to a state-of-the-art manufacturing machine. With the Lego brick, you don't need a ruler to place it, so the child can make something larger than themselves. The manufacturing machine has a build volume. With the Lego brick, the tower the child makes is more accurate than their motor control because you can detect and correct errors in their joints. When you run a 3D printer like the one behind me, if something goes wrong, errors accumulate and you get a tangle of spaghetti. You can join bricks made out of dissimilar materials to make complex functionality. It's very hard to print multi-material systems with very different properties. And crucially, you can unbuild. There's no Lego trash. You don't throw it away. You take it apart and reuse the parts. 3D printing output you need to grind up, and if it's very hard to reuse it again. Those are properties of Lego bricks. They're properties of amino acids. They're properties of what we call digital materials, and they're the same properties that made digital computing and communication possible. Phones got worse with distance. Analog computers got worse with time. The ability to detect and correct errors in code is what led to that digital. What we're now learning is the essence of these 8 orders of magnitude is actually this deep sense of digital all the way into the materials. In this talk, I've taken you, we started with the COVID pandemic, went to Fab Labs today, went to the machines making them, went to the machines making the machines to deploy those coming out in the near future, the assemblers, which right now are looking at extremes of performance, like jumbo jets or spaceships, but will become more widely accessible, and then the basic research on this fundamental self-assembly. And Skylar will tell you much more about self-assembly. If you take that 50-year roadmap, it has profound implications ultimately today. So on the right is a book I wrote describing everything I went through with my younger brother, Alan, who ran the biggest video game studio at Activision, and then reached the limit of blowing people up, and he started Eline Media to do games for education and social change. And so they've done amazing games with Alaska Natives, or to do cultural storytelling, or BBC on the oceans. And so he's an expert in digital and mass media. My older brother ran the National Labor Relations Organization as an expert in the future of work. They would hear me give a talk like I just gave, and while the rest of the audience would applaud, they would groan, because they would see how naive I'm being about everything that went wrong after Gordon Moore's graph. Gordon Moore got everything right technically, but what he got wrong was he missed spam and fake news and income inequality and all the issues we've been struggling with. And so this book was about, if we're headed to 50 years of the scaling, how do we shape it now to not reinvent spam and fake news and all of that, going from digital to physical? On the left is a policy piece we wrote about that. And so if you take among the most sensitive issues right now, that in pre-pandemic, that include tariffs, jobs, income inequality, they all assume an equivalent, that jobs equals work equals money equals consumption. But that's a relatively recent state of affairs. And so what I'm showing here is a Fab Lab in Vestmannaeyjar, Iceland. It's a tiny volcanic island off the coast of Iceland, beautifully set up with all the tools for digital fabrication. If you go in there and you produce the kind of products you buy today, it's not utopia, it's not free. You could do it for yourself. You could do it for family and friends. You could do it for barter, for exchange. You could do it for a small business. There's a false dichotomy between do-it-yourself and mass manufacturing. If you look at the evolution of printing or of music or of software, what happened to each of them is filling in the space exactly between do-it-yourself and volume for each of them. And that space in between is where so much of the interesting activity has been. In the same sense, if you can send data, think globally, digitally, but fabricate locally, it means you don't need global supply chains to ship products. You just need selected global supply chains for the building blocks for it. You don't need a lot of the infrastructure of the ports and highways, a lot of the infrastructure of the taxes, a lot of just how government works, how society organized assumes we're shipping bits rather than atoms. Once you have the means to change it, it fundamentally changes those relationships. It turns it on its side. Blair Evans runs a really interesting set of labs in Detroit, where explicitly a third of the time in the lab they manage for traditional economic activity. A third of the time is kind of post-economic activity. It's barter exchange for the good of the community. And a third of the time is for the well-being, not for economic activity, like G&H in Bhutan. It's for learning, it's for improving the community. And really viewing that as a very different way to think about how society functions, rather than segregating work, education, play, industry as separate tasks, how to bring them together. And once again, don't think of a false dichotomy of do-it-yourself or volume manufacturing. They all have a role, but by integrating them in the middle, there's a really interesting collaboration. If you go back to all the mini computer companies that failed, there's a lot of mid-sized manufacturers who won't survive this transition. There's a lot of big companies that are very thoughtfully engaging in what is their role in this world. And there's a lot of new businesses emerging, but with very different business models that have much more to do with the social return. And this ultimately is the real impact of rapid prototyping in the pandemic. Variously, it's credited to Rahm Emanuel and Winston Churchill, the notion of not wasting a good crisis. And what we're beginning to see emerging is the economy is broken. There's so much unemployment. There's so many businesses in distress. There's a real opportunity by expanding access to the means for digital fabrication to not just restart the economy as it was, but really embrace this opportunity to make it much more responsive, much more accessible, much more local. And so much of the work in the collaboration I showed you at the beginning is still very busy on the immediate pandemic response. It's transitioning towards test and measurement to help do the tracking. But the meta project emerging is how we can use this to integrate rapid prototyping, not just to make prototypes for mass production, but throughout the society to really rebuild a different sort of economy that's more accessible and inclusive. It's not just a whoosh. We've really seen this happen in these interesting pockets I've shared you. There's an opportunity now to do it at much more scale. So with that, there's background in each of these. I can share this presentation, and I'll be happy to discuss now for the remaining time.
Okay, we have a couple of panelists on that actually have the capability of asking some of the questions. So I don't know if some of the panelists have some questions. John Roberts.
Hi, Neil. Fantastic talk, mind-bending. Maybe not for your brothers, but for probably most of the rest of us. I have a question about what your vision is in terms of impact on resilience, this notion of communities, whatever that means, being self-sufficient.
Yeah, so there's been an interesting connection. The labs, I set up one, dear former mentor at MIT, Bill Mitchell, suggested I talk to Mel Smith, a pioneering community activist in Boston. That's where we set up the first Fab Lab. But then there was a Ghanaian connection that led to one in Sekondi Takoradi. Then from Ghana, there was a South African connection that led to one in Pretoria. And that started this pipeline of them doubling. We didn't plan that. But there's been a really interesting connection with where they've gone and communities in stress. And so I showed the example of in Northern Ireland, there are what are called the peace walls that are really sort of the war walls between Protestant and Catholic communities. We set up, they sort of pulled us in to set up labs there where people from both sides of the, in quotes, peace walls could come together and collaborate in the community. In the example I showed you in Alaska, fabulous, amazing cultural traditions, but terrible Alaska Natives, alcoholism, suicide, unemployment, and the kids were spending their time sitting at computer screens. This is now mixing traditional crafts and materials with modern digital fabrication. For a number of years, we ran a lab in Jalalabad in Afghanistan, right in the middle of a war zone. In this global Fab Academy I teach, we have really remarkable students from refugee camps in Jordan participating. And so the labs have been sort of attracted to and flourishing in these stressed communities. But what's, I'd say the lesson I've learned from that is they're clearly relevant to it. And there's a whole package, like in the refugee camps, of no economic opportunity or entertainment or educational opportunity. And sort of there wasn't great things on offer for it, for which this is very relevant. But there's kind of what the surprise for me has been, I had a naive sense that like poor places would use these to do poor things and rich places would use them to do rich things. Instead, what we find is they get exactly the same profile of bright, inventive people who come to MIT come to these places. But MIT can fit a few thousand people and there's a few billion people. It's exactly the same bright, inventive profile, and they use them exactly in the same way. Yeah, MIT people use MIT for research, for big business, for startups, for play, for art. And it's that same mix of activities. And so you don't have to recreate the Industrial Revolution all over again. In the same way Africa went right to mobile phones, these are kind of going right to this integration of all of those skills. And so the conjecture is that that'll work on an even bigger scale as we go in this powers of 10. Right now we're at thousands of these labs and we're just beginning to pivot towards what the transition like to go towards millions of them.
Beautiful, thank you. Thank you very much.
I have a question I want to take you from the audience. One of the questions that came up quite often is, do these Fab Labs actually include biological manufacturing platforms?
Yeah, so there's a beautiful recursion. With my colleague, George Church, who's the world's greatest geneticist, he's a national treasure. He can teach a classroom of students at a time. And you obviously can't do biology in an online class. And so he saw the Fab Academy, and that led to the idea of a bio academy we've been running, where students roughly you use a Fab Lab to make a bio lab. And bio labs need things to like spin things around and heat and cool them and move pipettes around. And so Fab Labs can make a lot of the instrumentation in a bio lab. Then you need the reagents in the bio lab. And so that my first class is called How to Make Almost Anything. It inspired the class How to Grow Almost Anything. And that's using Fab Labs to make bio labs to teach biotechnology, and then in turn closing the loop by using biotechnology as a process in the Fab Lab. This one went through a really interesting sequence. How to Make Almost Anything at MIT, which started in my lab. It actually has grown to 3 other labs at MIT in electrical engineering, computer science, architecture, and there's even a Harvard lab for my class at MIT. On the on-campus version, that became the Global Fab Academy. How to Grow Almost Anything started as a global class through the Fab Labs, and then Harvard and MIT students were asking, how come we don't get to do that? So it actually came backwards onto campus as a current class that George Church, Dave Kong, a number of colleagues are running. And so there is this deep connection between Fab Labs making biolabs that go in both directions. So absolutely, yes.
I see that Skylar actually has joined us, and he had a question for you.
Yeah, Neil, I was wondering if you could talk a little bit about how you see this moment, specifically with COVID, as a case study. Like I've been thinking about, traditional manufacturing supply chains are, either shut down or very difficult at the moment. And it shows the vulnerability that you're talking about. And maybe this is the moment that we can go from what most people think of as DIY at home, small scale manufacturing to sending digital, fabricating local. Do you see that as well?
Oh, so yeah, this is what I'm spending much of my time on. The do-it-yourself is inspiring, but relatively ineffective. One person with one 3D printer just can't make much impact. Mass manufacturing has struggled for how it pivots to it. In the space in between, what's spun up is an amazing collaboration. So these weekly meetings I've been running of this working group that ranges from state-of-the-art research in big industry to community groups to government has led to collaborations that were maybe far in the future happening at high speed. And so let's see, was it just last night, Dale Daugherty, founder of Make, did an interview with me and a group of these people, and there's a nice video from that we can share exactly on Skylar's question. But things like tools from the CBA lab we sent to Artisans Asylum, a makerspace in Somerville, and now they're pumping out masks and gowns. A colleague, Danny Beasley in the Bay Area, has taken makerspaces all over them, help curate best practices, and having them become coordinated production. So it's not self-organizing. It's sort of naive self-organization doesn't work. You always need to curate it. One of the interesting things Danny is doing is he's organizing them as a worker-owned cooperative. So it's not just charity, but building a sustainable business model around it. One of the most active participants in this working group is Megan Smith, who did range of community government things at Google, became Obama's CTO. Now she's focused on mixing the best of public and private partnerships and really embracing this, because unlike anything I've been part of, it's just driving collaborations. We're all working together in a way we've never worked together before. And so that's why Megan, we all want to stay a little bit ahead of where it's headed. So not just meeting the immediate needs, but thinking about how we can maintain those kinds of collaborations. It's a profound teachable moment in the impact of relying on remote global supply chains. And it's not back to the past, it's sort of back to the future of what does it mean to get access to these locally. I mean, let's see, I'd say three focal things I see. One is propagating best practices in the machine building so that you really deploy best, not worst practices. One is this notion of universal access, really accepting everybody should have access to it. And then one is, it takes a lot of research to learn, once you have the tools, what to make with them. And so you really need to curate that. And so this is a profound time to tackle all of those things. It's, it is a hopeful message that we may not come back to where we were. It really is a chance to build back better. Absolutely.
Here is another question which is interesting from the audience, from Susanna. So the construction method describes, do they also allow for recycling or deconstructing of the material?
So yeah, this is something I'm religious about. There's no trash in biology. In a forest, your parts are disassembled and reused. Trash is an analog concept. Trash means materials don't have enough information to reuse their components. Recycling is a sign of failure. It's a sign that you need, these horrible jobs of people who have to look through trash and pick things out because there isn't information in the material. The essence of biology is materials contain information that guides them through their life cycle. And so all of the projects I showed, I started at so a Fab Lab is digital fabrication in the sense that if you're outside the room, data comes in and a product comes out. But to do it, you needed 10 different machines. The machines making machines is one machine that can do the 10 functions, but it's still smushing material around. The assemblers the materials are becoming digital, but there still is a machine, and we end the roadmap where the machine and the materials merge. But to that key question, that's why central to this is the idea of materials being constructed from the assembly of simple building blocks that allow you to disassemble them. And so a term of art for these is metamaterials. If you look microscopically, it's not a continuous material, it's little building blocks. but it becomes a metamaterial that if you zoom out looks like a continuous material. And once you've coded its construction, it means you can unbuild as well as build. And in the short term, that's essential for the work we're doing with like Toyota on cars or Airbus on airplanes or NASA on spaceships, because it means you can find defects and you can fix them in a way that you can't today. But for the life cycle, it means the parts themselves are reusable and you can unbuild. You can build down capacity when you don't need it, for example. So that's central to this roadmap.
Oh, that's interesting. I see that Jose Ramos on our panel actually has a question. So
great. So I had my question related to exactly to this topic, and there's actually somebody who was asking a similar related issue, which is there's also, so you mentioned earlier that you're limited to the materials of biology on the biological realm. And now we're talking about, you were talking about how the raw materials are actually have to have themselves kind of building blocks so you can kind of deconstruct them. So there's a question there too as well in the Q&A, which relates to the software. So there's the issue of software that's going to drive, let's say, your super Fab Labs. And I would imagine then that the vision is that even the software itself gets generated kind of locally, right? Is that one of the goals as well? Because otherwise you're having to rely on an external vendor or an external software developer.
Right. So first, for the first part of your question, I did a really fun program. So I helped start an office for science in Hollywood, and I'm part of the bonus material for the movie The Martian, where they wanted to show how do you actually reboot a civilization? How do you create a civilization on Mars? And traditionally, the approach to what's called in situ resource utilization, ISRU, assumes a model. Somebody called Gingery wrote a wonderful series of books where book 1 is a charcoal furnace, book 2 is hand tools, and book 7 is a machine shop. And the assumption is you sort of have to do that on Mars. You have to go through all the stages of the Industrial Revolution. Based on this talk, what's emerging is you need to essentially create life in non-living materials. You need about 20 properties like conducting, insulating, semiconducting. You need to build them into these simple building blocks, and then you hierarchically compose them. And so it's really getting at, and that bonus material is getting at this amazing question of, and we're almost out of time, so I'll end with this. What are the minimum building blocks to bootstrap a technological civilization? In the short term for the pandemic, this conversation is how do we restart the economy? Ultimately, this is asking is what is the technological basis, minimum technological basis of a society? And so the last part I skimmed over is where does the software come from? So clearly the software is not distinct from the hardware. They're very deeply integrated. And to do this work during the pandemic, we've been doing a lot of work on the physics of the modeling. We've been working very closely with the leading software companies on exactly what you're alluding to. You can't write the software from scratch to place a billion things. The software has to write the software. But if you do it naively, it's a mess. And so again, this old curated part of the genome is how biology makes software that writes software. And that's what we're learning how to do for engineering. And that's one of the most active research projects I'm in right now. So we're up to 30 seconds from the end. So it may sound like a metaphor, but the planet goes 1,000 million billion trillion. Computing literally went 1,000 million billion trillion. I'm talking about 1 trillion Fab Labs, 1 trillion things with the capability of the 1952 NC mill. That's between today and 50 years from now, but there's profound implications today. And take away, rapid prototyping is not just a prototype, it's a fundamentally different way to organize society, and the pandemic is a great opportunity. And once again, I'm happy to follow up with anybody listening on any of this. In particular, these weekly COVID sessions, you can find them through gitlab.cba.mit.edu. All the content is public. You need to be a member to actively participate. And so with that, I think I've queued it up for Skylar, who he can tell you some of the great history of our shared background to pick up this thread of self-reproducing systems.